Hello everyone and welcome to Chapter 8. We're going to start with Lesson 8.1 on inverse variation. So there are a couple of vocabulary terms that we want to talk about. The first is direct variation. So we have direct variation in an equation if we have an equation that's written in this form. Y is equal to a times x. And please note that a can't be equal to 0 here because then y is equal to 0 and x just kind of goes away. There is another form of this same equation if we just rearrange things a little bit, and let me show you that because it's going to be helpful to us occasionally. So if we start with our equation but solve it for a, so I'm going to get a by itself by dividing both sides by x, and that's going to give me that a is equal to y over x. Okay, so that is another form of the same equation. All I did was rearrange it a little bit, and notice in this form we can see that our quotient, the result of dividing y by x, is some constant value a. So the quotient is constant. That constant a is called the constant of variation, and y is said to vary directly. So that term direct variation. So it's varying directly with x. Notice here that if we plugged in any number for x, a is a constant value, so our y is directly related through a. As we increase our x value, our y value also increases. If we decrease our x value, our y value also decreases. So x and y both either increase or decrease together. The opposite of that is called inverse variation. And inverse variation occurs when our equation looks a little different. Instead of a times x, we have a divided by x. So here is the other equation for inverse variation. We can also take this equation and rearrange it to solve for a. So if we have y is equal to a over x, in order to get a by itself, we would need to multiply both sides by by x. And we would get that a is equal to x times y. So notice in this case, what's constant is a product of x and y. So a multiplying of x and y gives us a constant value of a. So we'll be using both versions of these equations. Again, same thing, just a little rearranged as we go through our examples today. Our a is still the constant of variation, but this time a is varying inversely, or y is varying inversely with x. So vary inversely. All right, in this case, if we plug in bigger and bigger numbers for x, y is going to go down. And if we plug in smaller and smaller values for x, y is going to increase. So x increases as y decreases, and x decreases as y increases. All right, so that's inverse variation. So let's take a look at a couple of examples to help us determine whether we have direct or inverse variation. So in the case of this first example, we can see that x times y is equal to 5. So x times y is equal to a constant value. This is our a right here. And because that product of x and y is constant, we can look here at our inverse variation and see that that's the form of the equation we have. Our product of x and y is constant. So our product is equal to a constant. So we are looking at this one right here, that version of the equation. So we can see that we have inverse variation. All right. This next one, we've got x and y on different sides right now, and we can go from this particular version of the equation and rearrange it to get x and y on the same side. So let's do that. The first thing that I'm going to do is I want to move the 2 over to the right. So I am going to multiply by 2 in order to move it. So I will end up with y is equal to 2x. From this version of the equation, we can actually look up here and see that that is this equation right here with a value of 2 for a. So we can either stay with that version of the equation if you would prefer to rearrange it to have x and y on the other side. We can do that as well. So we could divide both sides by x and get that 2 is equal to y over x. So we can see distinctly that our quotient is a constant here. That means that we have direct variation. Again, most of you would have been able to tell that it was direct variation once we got to this point, but I just went ahead and rearranged it to solve for my constant for my a value, just to make it a little clearer if you needed that clarification. All right, this final example on this page shows that y is equal to x minus 4. I don't see any multiplying or dividing here. If I wanted to get x and y on the same side, I would be subtracting x from both sides to do that. So this is not multiplying or dividing. So that means that it's neither. Remember, it has to be either multiplying or dividing to get a constant in order for it to be inverse or direct variation. All right, let's go ahead and move on to page 2. And this time, instead of identifying inverse or direct variation from an equation, we're going to use a table of values. So let me just remind you that if we have our constant a is equal to y over x, so if the quotient is constant, then we have direct variation. And similarly, if we have our product being a constant, then we have inverse variation. So we're going to take these x and y values and figure out whether we have a direct or inverse or neither. So let's take a look at this first one. So let's go ahead and start with multiplying. So I'm going to use x times y and multiply across here. So 2 times negative 12, again multiplying x times y, I get negative 24. 4 times negative 6, also negative 24. Negative 24 here for 6 times negative 4, and another negative 24 there. So this is constant. We have the same exact value. So that means that we have inverse variation. Now I want to show you what happens when we do the quotient instead of the product. So if we take y of negative 12 and divide it by 2, I get negative 6. Here I'm going to get negative 6 over 4, negative 4 6. And again, we could reduce these fractions if you wanted to, but not really necessary. We can tell for sure that these are not constant. It's not all the same number. So we definitely don't have direct variation. We already concluded that we had inverse variation. So our answer is that this one is inverse. All right, let's do the same thing on this next one. So I will first do the product, which would tell me if we might have inverse variation. So 1 times 2 is 2. 2 times 4, 8. 3 times 8, 24, and 4 times 16, 64. This is not constant. So that means we don't have inverse variation. We cannot assume, though, that we have direct variation just because we don't have inverse. We need to check it and see. So let's say our quotient now, y over x. So if I have 2 divided by 1, I get 2. If I have 4 divided by 2, I also get 2. 8 divided by 3 doesn't reduce anymore. It's not going to reduce to a 2. And 16 divided by 4 is 4. This is also not constant. So what we can conclude here is that, in fact, we have neither. So 3 choices here: inverse, direct, or neither. This one ended up being neither. Let's check our last one. So again, I'm multiplying my x and y values together. So negative 4 times 20 is negative 80. And as I continue, I get negative 45, negative 20, negative 5. Not constant. It's not all the same value. All right, let's go ahead and do our quotient, y over x. And I get 20 divided by negative 4, y over x is negative 5. 15 divided by negative 3, negative 5. Negative 5, negative 5 when I continue that out. And so this is a constant value all the way across. So that means that we have a direct variation. All right, so remember, when the quotient is equal to a constant, it's direct. When the product is equal to a constant, it is inverse, but sometimes it can just be neither one. All right, let's go ahead and take a look at some examples where we actually have to write the equation given some values. So let's take a look at writing an inverse variation equation. So we are given variables x and y, and we're told that they vary inversely, okay? Remember, if it's inversely, that means that y is equal to a over x, or the other form of this is that a is equal to x times y. Okay, so we're going to use one or the other, in this case maybe even both of these forms of the equation. So let's go ahead and bubble these again just to remind us that this is an important equation to know. All right, so we want to write an equation that relates x and y, and then find y when x is equal to negative 2. So we know y and we know x. What we don't know right now is our a, our constant value, but we know one particular point at 3, 4 as our ordered pair. So in order to find a, I'm going to use the version of the equation that's already solved for a. I'm going to say that a is equal to x times y, but I know an x and a y. I know that y is 4 when x is 3. So I can say that a is equal to 3 times 4, which gives me a value of 12. Okay, so now I know my constant of variation, and I can write my actual equation, the generic equation for this. So I know that y is equal to 12 over x. There is my equation right there. That's part 1. Part 2 is that we want to know what y is when x is equal to negative 2. Well, all we have to do is plug in x equals negative 2 into this equation that we just wrote. So y is equal to 12 over negative 2, or y is equal to negative 6 when you simplify that. Okay, so we wrote our equation by figuring out what a was given one specific point, and then we were able to solve for another specific point. Let's do this one more time. I would suggest you pause the video here and try this one on your own, then come back and see how you did. So pause now. Okay, we're back. This time we are still told that we're varying inversely, and y is 8 when x is negative 4. Since we have inverse variation, we are using this same equation up here that we did before, that y is equal to a over x, or a is equal to x times y. Since we want to find what a is, I'm going to use that version of the equation, that a is equal to x times y. But I know one specific point where x is 4, y is 8, so my a value is equal to 32. And I can use that to write my actual equation, y is equal to 32 over x. Again, part 1 is done. I have written the equation. Now, I just need to plug in when x is negative 16 and find out what y will be equal to. So y is equal to 32 divided by negative 16. Again, we're just evaluating the equation when x is equal to 16. And I'm going to get that y is equal to negative 2. All right, let's look at a real-world problem here. This is something that can be used in a lot of ways. We are going to talk about building a playground. All right, so we're going to build a playground, and we have some volunteers. The time t in hours that it takes a group of volunteers to build a playground is going to vary inversely with the number of people that are helping. And we know one point on this inverse. We know that it takes a group of 10 volunteers 8 hours to build the playground. So we're going to go through the same steps that we just did on writing an inverse equation and solving it. So we can write an equation showing how the time changes as the number of volunteers changes and solve that for a so that we know what a is equal to. So we're used to using x's and y's. We have y is equal to a over x, or a is equal to x times y. However, in this particular example, we are using t and n, the number n for number of volunteers. So our x value is n, our y value is going to be substituted with t. So let's go ahead and rewrite this in the form that we need for this real world problem. X and y actually have meaning now. They are time and number of volunteers. So we can say that time varies inversely with the number of volunteers. The more volunteers you have, the less time it's going to take. Or the other thing we can say is that our constant is equal to the time times the number of volunteers. All right, so let's go ahead and solve for a. That was the second part. So this is our equation right here. But we want to know what a is. So we can say that a is equal to t times n and plug in the values that we know. We know that it takes 8 hours when we have 10 volunteers. So our coefficient of variation, a, is equal to 80. That's our constant. All right, so if we wanted to write our final equation, t is equal to 80 over n. Just like that. All right, so we've written our equation in generic form, we've written it in specific form with the 80. Now we want to create a table here that shows us how the time changes as we add more volunteers. So again, we are just evaluating the equation we just came up with, that t is equal to 80 over n, and we're evaluating it for specific values of n. So the first value is already given for us, that when we have 10 volunteers, it takes 8 hours. But now we want to find out what happens at other values. So when we have an n value, a number of volunteers, equal to 15, it's only going to take 5.3 hours. And that 3 is repeating if you stick that in your calculator, so I'll go ahead and note that. Whenever we have 20 people working on it, it only takes 4. When we have 25 people, see, over 25, then that is 3.2. And finally, the last value we need is 30, and that's going to give us 2.666 repeating. So let's go ahead and transfer those numbers to our graph. And that answers B. All right, so you can see that the time starts going down as the number of volunteers goes up. All right, so now we just want to kind of describe in words what happens to the time that it takes when the number of volunteers increases. Well, looking at the table, we can see, or we actually could have even indicated it at the very beginning because we knew that it was inverse variation. We were told that in the problem statement, that the time required to build the playground decreases as the volunteers, as the volunteers increases. All right, so inverse variation tells us that as one value goes up, the other one must go down. This concludes our lesson. Thanks for watching.